All right, so let's talk about exponents, specifically exponential growth and decay. So we're coming hopefully towards the end of a pandemic. Don't want to call it too early, but that has a lot to do with exponential growth and decay. So can anyone think of some scenarios? So make a list of some scenarios that model exponential growth or decay. So it's very common in the world. Yeah. Yeah, excellent. So like COVID-19, like pandemic, like how the cases spread. Yeah. Excellent. That's very relevant one. So yeah, if one person has COVID, the first person to have it, all right, it's not going to spread right away, but now they could give it to people. So let's say they give it to 2 people. Now those 2 people could give it to 2 people. So now 4 people have it. And then those 4 people could each give it to 2 people. Now 8 people have it. And this is why early in the pandemic, maybe it wasn't taken too seriously because the cases were low. But once exponential growth is deceiving in a way, like it starts off slow, but then it gets that big pretty fast, as we'll see. Who trivia, or raise your hand if I give you an option. If I said, all right, for a whole year, I'll give you $1 million a month. Raise your hand if you would take that deal. And without knowing the other deal. Yeah. Okay. Okay, now, the other option is I'll give you a penny a day, but I'll double it every day.
Oh, I'll take that one.
You take that one, yeah. So if we look at it, by like the second or third month, you'd be making well over $1 million. Yeah. So, but it's we start with $1 million, you would think, oh, $1 million a month, that's a sweet deal. But a penny, that's not a lot. But if you double it every day, it will get a lot within like 31 days. All right, any other scenarios where exponential growth plays into the real world? Yeah. Yeah, definitely. Like companies' growth, like they start off with like 1 factory and then they get 2, and now because they have 2 factories, they're bringing in more revenue. Now they can afford like 2 more. So yeah, like growth of a company. Excellent. Anything else? Very good. So exponential growth could also be exponential decay, like how much your car loses value. So like I'll call that depreciating assets. So like a car losing value. Excellent. So they say like a car loses about 6% of its value every year. So that doesn't mean you lose like 6% of the original price. It's like if the car was like $20,000, the next year it'll be worth 94% of that because that's 6% less than 100. And let me pull up the calculator. So like if we had a car that was worth $20,000 and it lost 6% a year, that'd be 1 minus 0.06. All right, so after 1 year, it's worth that much. And then the next year, so that's 0.94, it's now down to that much. So yeah, it's and it'll start leveling out as it gets closer to 0. So in the first year, it loses like a little over $1,000. The next year, it loses slightly less and then slightly less as it approaches 0. Any other things you think of? Those are pretty good. Yeah. Yeah, interest. All right, so at some point, we'll do a lesson where we look at like saving money and how it's important to save young, because when you save, the interest rate might be low, but over time, like even if you get 2% a year, it adds up pretty quickly. And most things you can invest in long term, like if you could invest in like funds that model the whole stock market, like generally they do lose money some years, but in the long run you gain like up to like 6-7% a year. Which if you start saving every paycheck when you first start working, so like when you're in your early 20s, by the time you're in your late 50s, you should have like a nice savings. So very important to save and save young, even if it's a little bit, because interest will compound very quickly. So yeah, so like bank accounts, / compound interest. All right, those are the big ones. And there's other ones, but that's another one that comes to mind is half-life of like, let's say you take like an Advil. An Advil has a half-life of like about 2 hours. So if you take like 100 milligram Advil, after 2 hours, like 50 milligrams would be left. And then after another 2 hours, so after 4 hours, 25% will be left. And then every half-life time period, it gets cut in half. So theoretically, you always have a little bit of that left in your system, but practically speaking, like your body probably will just eliminate all of it eventually. All right, awesome. All right, so here are some models. So for exponential growth, one of them that we can use, we'll say it's y equals a times 1 plus r to the t power. All right, so that's if like that's more like something's getting compounded like every year or every minute. R is the rate of increase or decrease. So let's say that you bought like an antique car that's an older car, it's actually gaining value. All right, let's say it gains 5% value every year, then this part would be like 1.05 because it's 5% more than 100%. So if it's an appreciating asset, it still has 100% of its original value plus whatever it's increasing or decreasing. All right, and then for like compound interest, you can also use this model, A equals P times 1 plus R over N, and then to the N times T power. So these are pretty similar formulas. The only difference are like instead of a Y, I use an A. Instead of an A, I use the P. And the reason why is this is like the amount in an account. Y could be anything. A here is just like a letter because it's the first letter of the alphabet. Here, P stands for principal. Principal represents like what you start out with in an account. And then R is the rate still, but sometimes things are compounded multiple times per year. So if let's say you had a bank account that gained 12% interest every month, but it was 12% annual interest, that means you get 1% a month versus 12% at the end of every year. All right. And we'll explain that when we do examples. And there's also compounded continuously, which would be A equals P times E to the RT power. So when things get compounded like infinite amount of times in a year, so basically if you took this formula and looked at what happened as n approached infinity, you would get this formula. But you just have to know how to use it. We'll talk more about why it works, but I'll say like this is for continuously or compounded continuously. This would be compounded n times per period. And this is more just like simple, like just compounded once per period. All right, and then decay just means losing value. So the only difference if this was decay would be that now you would subtract the rate, like what it's losing. So that'd be A times 1 minus R to the T power. All right. And same thing here, like R would just be negative. Or you could do minus R over N to the NT power. All right, and here it'd be R would be negative. All right, and then R is sort of like this is exponential growth. It would look like this. If I drew like an X and Y axis. And then decay would look like this, where it gets closer to the 0. And if you look at those two together, it's like one's reflected over the Y-axis. And that should make sense because the only thing we're doing is we're negating R, which is sort of like the X value here. And if you negate the X value, that's going to reflect it over the Y-axis. All right, so I know it's confusing when you're just learning things without context, so let's just keep these here, and I promise I'll explain them more as we go through problems. All right, so let's try number 1. All right, so number one, we have a certain type of, I wish I could zoom in more for you guys, but I can't really get it to zoom in. I'm trying. All right, that's the best I could do. Maybe I could push this camera closer. It's not bad. If I get off the screen, let me know. So a certain type of bacteria gives a favorable growth medium. Given a favorable growth medium, doubles population every hour. Given that there are approximately 100 bacteria to start with, write a function that models the growth of the bacteria. All right, so a lot of times in these formulas, T is going to be in years, but it doesn't have to be in years. That's why I said like per period. The time period can be whatever you want, but you want people to know what it is. So we'll let T be years, but we're going to let T be in hours, and it's important to denote that. All right, so T is in hours. All right. Now, model the growth of the bacteria if we start with 100 bacteria. All right, now A or P, these numbers in front of parentheses is always going to be like the initial amount. It's always going to be, in this case, it'd be 100. So we have y equals 100. And when I'm done, I'll explain why that's the case, but I have to have the rest of the formula to make sense. All right, now if it doubles every hour, what do you think should go inside the parentheses? That's a good guess, but that would be like if it went up by like 5% every hour, compounded twice per hour, then we would make n equal 2. But this, it doesn't say it's compounded multiple times per hour, it's just doubling every hour. So we can use one of the first two. Like we don't have, this is only when it says it's compounded a certain amount of times. All right, but it's doubling. So I'll just put R here for now. I'll just put B here for a second. You don't have to do this part. But if you plugged in 0, like T equals 0, then this would give us Y equals 100, which makes sense because we start with, that's T equals 0, we start with Y equals 100. All right, and now if we wanted to double after 1 hour, like what would B be, or what? How much bacteria should be there after 1 hour if it doubles every hour? 200, right? So what would B have to be in order to make that 200? Just a 2, right? So doubling every hour means it gains 100% every hour. So if you were to use this formula, R would be 100%. So it would be 1 plus 1, which gives us this model where the base is just 2. So if it says it doubles every hour and T is in hours, you could just make the base of your exponent 2. If it tripled every hour, that would be 3. If it went up 25% every hour, then it would be 1.25. Not block. Let me know if we're blocking. All right, cool. So how much bacteria will be left in a day and a half? So this is why we had to denote that T was in hours, because now what we have to plug in for T to find out how much bacteria is in 1 day and a half. 36, because that would be 36 hours. Very good. So it's going to get quite large, so we're not going to do that without a calculator. So now we're going to get our calculator out. And we'll type it in. We'll go 100 times 2 to the 36th power. That's quite a large number. There's a lot of bacteria. So that would be 6, 8, 7, 1, 9. Wait a minute, that's my phone number. No, just kidding. 4, 7, 6, 3, 3600. So it'd be 1. That's a milli. That's a billy. That's a trilly. 6.8 trillions. It's a lot of bacteria. I know bacteria are small, but I feel like if there was that many bacteria, you'd be able to see them, right?
How much is like on your body?
Whoa. Not on my body. Don't talk about that. I got no bacteria. Yeah, there's good and bad bacteria. All right, nice. All right, cool. All right, let's do it. Let's flip the page. All right, stop me if you have questions. Do I have questions here? No. All right. You know what? I'm going to turn one of the lights off at the front so you can see the board a little better. All right, so a quantity of insulin used to regulate sugar in the bloodstream breaks down by about 5% each minute. A body weight adjusted dose is generally 10 units. All right, so write a function representing the dose that remains. All right, so a couple things I noticed. All right, 5% each minute. So our rate of decay is in minutes. So we're gonna let T be in minutes. All right, and then it breaks down by about 5%. So that means R is going to be like -5 or 0.05 because it's decreasing by 5% every minute. And this is going to be like our initial amount, what we start with. So like 10 units. So if I were to write a model here, I would say Y is equal to 10. So that coefficient is always what you start with, times the rate, which would be 1 minus 0.05. So don't do the double negative, like don't subtract 0.05, like either add negative 0.05 or subtract positive 0.05. Basically, if it's decaying, you want this base to be less than 1. And if it's growing, you want that to be greater than 1. All right, because look, I could show you real quick on Desmositos. So y equals, we'll say, just a to the x power. Add a slider. So notice how when a is greater than 1, it's exponential growth. And once it's in between 0 or 1, it's decay. And if it's negative, then that's never going to happen. All right, and if it's 1, it's constant because you're just multiplying something by 1 each time, so it's not going to change. Okay, so this would be to the t power, where t is in minutes. So we got y equals 10 times 0.95 to the t power. So that 0.95 means, like, yes, the body breaks down 5% of the insulin each minute, but 95 means that it's still retaining 95% of the insulin each minute. All right, so I always think of this as like the retention rate, like what's actually staying, whether it's positive or negative rate. That's always what's retaining. All right, so there is our model. So how much remains after 10 minutes? So since t is in minutes, we can just plug in t for 10. And now we'll use our calculator. So y equals 10 times 0.95 to the 10th power. All right, so about 5.987. So it doesn't say what to round to. I would really just round to like 1 or 2 decimal places. I would never round to the whole number unless it says it. So we'll say that equals around, we'll go 5.99. And that would be in units, because the original amount 10 was in units. All right, so how long does it take for half the dose to remain? All right, so there's a few ways we could do this, but we want to set it up first as like an equation. So like y equals 10 times 0.95 to the t power is our model. And since we started off with 10 units, we want to know when there will be half of that. So like when there will be 5 units. So we have to solve this equation. So we have 10 times 0.95 to the t power equals 5. So the way you could do that, and I'll show you other ways when we learn logs, which you probably remember from Algebra 2, and we will practice that. But for now, you could, and I'll show you how to do it with logs, but you could just graph both of these and see where they intersect. So I'm going to take this y equals 10 times 0.95 to the x power, because the calculator won't take t, it'll only take x. Then also graph y equals 5 and find their intersection. So on my calculator, I'm going to add a new page that's a graph. And then graph 10 times 0.95 to the x power. And you can see part of the graph right there. And if we zoom out, we see more of it. So what's great about a graph is that you could trace it. And you can see like, all right, after we start off with 10, after 1 hour, there's 9.5 units remaining. And then after 2 hours, 9. And then you could keep arrowing over. And you can use this trace function to estimate your answer. So it'll take like around like 13.5 hours for it to be half. But to get that number more exact, what you don't want to do is graph the other side of the equation. Graph y equals 5 as well. And you could solve any equation like this by graphing both sides of the equation and finding the intersection. So analyze graph intersection. All right, and you get this point 13.5 comma 5, which means if you plug 13.5 in for x into the blue function, it'll equal 5. And if you plug 13.5 into the red function, you'll also get 5. So 13.5 is the x value that makes both sides equal. So you're going to want to know how to do that to solve equations like this, and simply graph both sides to see where they intersect. All right, so we got this, and then that, and then they intersect right here. That was a bad picture, but they intersect at 13.5 comma 5. I did that on the calc. So our answer is going to be t equals 13.5, and then always include the units. So that's in minutes. Oh, I got a question. Let's go. Are both questions soon? Sure. Sorry about the page. Yeah, so both of these equations are the same. I just simplified 1 minus 0.05 to 0.95. All right. No. No, it was a great question. Don't be hard on yourself. Oh, good. Yeah, so you could definitely use log. So yeah, so just I know coming up in our lesson plans, like we're gonna go over log. So like I always assume you know nothing except what I tell you, which just is like a safe way of teaching. So I don't assume too much, but that's great. And you should, that's good, you know, from physics and stuff. So yeah, if you wanted to solve this with logs, you want to isolate this part first. So like divide both sides by 10. So you get 0.95 to the t power equals 1/2 if you divide both sides by 10. Then in log form, this is your base, this is your answer, and that's your exponent. So in log form, it goes base, answer, exponent. So like the log base 95.95 of 1/2, if you type that into the calculator, it would equal 13.5. I know you can barely see that. I wish there's something I could do about it. Maybe if I turn this lamp on, it'll work. Oh, the lamp was on the whole time. I think that's worse. I wish I could zoom in. I have no idea how to zoom in on this thing. That helps a little bit. That helps a lot, actually. Yep. All right. Ooh, Beanie Babies. You guys know about Beanie Babies? TY Beanie Babies? Yeah, they're aware of their existence. They were big when I was like elementary school. Everyone thought they were gonna get rich off of them, and then no one did. I still hold on to mine. I got my Princess Diana Beanie Baby. I got the one that they sold at the David Wells Perfect Game. Yeah, they were a big deal, but never really caught on. But anyway. Yeah, maybe they printed too many of them. Like that's what happened with baseball cards. They were really valuable, and then like they started printing too many of them when they were like a Ken Griffey Jr. card was like super valuable, and then the company was like, well, let's just print a bunch of them. Did not realize that they flooded the market with them, and no one wants them anymore.
Yeah, that's some problems with reprints.
Yeah, they're making a comeback though. They're more controlled.
Dude, that Pokemon card was expensive.
Yeah, I know. I was not into Pokemon, but I had some friends who were, and they're searching for their cards.
I didn't sell my card a few years ago. I'm so mad.
Yeah, I know. That was a nice thing. That was a nice thing. All right. So on the peak of the beanbag animal fad, one sales representative sold 12,000 of the animals in 1 month. Each month after, the rep sold 20% fewer animals. All right. So how many beanbag animals did the rep sell in the 6th month? So since we're dealing like in months, so like each month he sold 20% fewer animals. That means we're going to let T be in months and R is going to be like negative 0.2 because that's a 20% decrease. So right at the peak of the fad, you sold 12,000. So that would be like our starting amount, 12,000. So we got Y is equal to 12,000 times 1 minus 0.2 to the T power. So that T is in months, which simplifies to Y equals 12,000 times 0.8 to the T power. So that means 0.8, yeah, he sold 20% less each month, but he still sold 80% of what he sold in the previous month. So to find out how much he sold in the 6th month, since T is in months, we'll do Y equals 12,000 times 0.8 to the 6th power. And then now we're just going to type that into our calculator. So 12,000 times 0.8 to the 6th power. And that would be, in the 6th month, he sold 3,145 Beanie Babies, roughly. So we'll just estimate it, and we'll round up to 0.6. So for something like a Beanie Baby where you can't sell half of it, I know I just said don't round to the nearest whole number, but if it's something that can't be like cut in half, then you can round to a whole number and put a little squiggly equal sign to show that it's approximation. All right, so in which month did the rep first sell fewer than 1,000 animals? So we're looking for the solution to this equation. Like when will 12,000 times 0.8 to the 6th power equal 1,000? So you could solve this by graphing both sides and seeing where they intersect. All right, you could solve this by, oh, I put a 6 there. I should not have done that. Let me fix that. This right here should be a T, not a 6. So we have to figure out like what's the first month where this is less than 1,000. So really, we're actually looking for like when is this less than 1,000, not when does it equal 1,000. So sorry, 2 little mistakes, my bad. All right, so I just showed you could graph both sides and look at it that way. All right, or I'm not going to hate on you if you do this either. Like if you take this model and be like, all right, well after 6 months he sold 3,000. So let's see how much he sold after 8 months. All right, it's closer to 1,000. Let's jump to 10 months. All right, let's jump to 11 months. All right, still over 1,000, 12 months. All right, so we can see after 12 months, that's the first time it's less than 1,000. So there's no shame in doing that. I did very well in the SAT doing that many times, just like guessing and checking. And I feel like it's bad. It's kind of gets like bad connotation to it, but guessing and checking is fine. Just sometimes there's better ways to do it. All right, so in which month did he sell fewer than 1,000 animals? That'd be the 12th month. Cool. All right, a couple more that I want to go through. 2 more. All right, so in 1626, the Dutch bought Manhattan Island, now part of New York City, for $24 worth of merchandise. Suppose that instead, the $24 had been invested into an account that paid 3.5% interest each year. Find the balance in 2019. All right. So I feel like buying New York City was a pretty good investment, but I'm guessing maybe this could be a better one. So let's see. So this is an interest problem. So it's 3.5% each year. So R will equal 0.035. All right, 24 is the initial amount. So that's going to be P, the principal. And we're going to use this model here. A equals P times 1 plus R over N to the NT power. Now, since N is equal to 1, because it says it got compounded each year, it doesn't say like how many times per year, you can assume N is equal to 1. So if you were to plug N equals 1 into here, that would become A equals P times 1 plus R to the T power, which is exactly the same model that we've been using. It's just instead of a Y and an A, we got an A and a P. You want to hear a grocery store joke that my dad used to tell me? Because he used to work in the grocery game. So did you guys hear about A and P in Stop and Shop? Did you hear about them? They're merging. They're gonna call it Stop and P. All right. Anyway, I'm here all night. Tip your waitresses. Okay. So now we're just gonna plug in. So we got P, we got R. All right, we need T. So T, we'll say T is in years because it's each year. And we got to figure out like, all right, from 2019 to 1626, what is that, like 400 minus 7, so 393 years? I think I did, no, that doesn't make sense.
I can do 2019 minus number to 16.
Yeah, I'll just do it. I'm bad at mental math. I know, I'm a math teacher. Shut up. I'm just not good at it. I'll make you guys do mental math. Oh, I was right the first time. All right, I am good at mental math. I'm just not confident in my abilities. All right, 393. Okay. So let's plug stuff in. Plug and chug, baby. So A is equal to 24 times 1 plus 0.035 to the 393rd power. All right, so let's see. With inflation and everything, how much money that'd be worth today. So 24 times 1 plus 0.035 to the 393rd power. All right, and that comes out to about 17 million, which I feel like buying New York was a better investment. Pretty sure New York is worth more than 17 million.
Yeah.
Pretty sure there are buildings that are worth way more than that in New York. So since it's money, I'm going to round to 2 places. So I'm going to do 0.09. So good job, Dutch. All right, excelente. Boom. All right. Good question. One more. So in 2006, 80 deer were introduced into a wildlife refuge. By 2020, the population had grown to 180 deer. The population was growing exponentially. Write an algebraic function, n of t, representing the population of the deer over time. Okay, so let's try it. So what we're going to do is we're going to since we're dealing in years here, I'm going to let t equal be in years. And we're going to use this model here. A equals, or y equals A times B, or y equals A, yeah, times B to the t power. Now, I know that's not one of the formulas that I had on the front page, but we could just let B equal like 1 plus R. It doesn't have to be like, it could just be one number instead of writing it as 2 things being added. All right, so we're going to let 2006 be t equals 0 because that's the first piece of information that we have. So it's going to be easiest if we start there. So when t equals 0, y is going to be 80. And then 2012, that's when the world was supposed to end. Y equals 6. Oh, wait, when t equals 6, because that's 6 years from 2006. All right, y is equal to 180. All right, so now we're going to plug stuff in and see what happens. So if I plug in these points, 80 for y, and then 0 for t, b to the 0 power is just 1. So we get 80 is equal to a. So now in our formula, we now have y equals 80 times b to the t power. So by giving you the first amount of deer, that allowed you to find a. Now we have to find b, so we can use this other point, plug in 6 for t and 180 for y, and then we can solve for b. So if we plug in these points, 180 for y equals 80 times b to the 6th power. So now we got to solve for b. So it's 80 times b to the 6th power. So we get rid of the times by dividing both sides by 80. So 18 over 8 is 9 over 4. And that's equal to t to the 6th. Or not t, b to the 6th, sorry. All right, and now, any ideas how we can get b alone?
6 root hexaroot. I don't know.
Yeah, you're right. 6 rooted. Or like another way to think about it is you can raise both sides to the 1/6 power. It's the same thing. Either way, we get b is equal to 9/4 to the 1/6 power, which we could find on our calculator. So 9 over 4, we got to put that whole thing in parentheses and raise it to the 1/6 power. Oh, I don't want that. What am I doing? 9/4 to the 1/6 power. Now my calculator is going to be obnoxiously specific and give me the exact answer unless I hit Control equals, and then I get that rate. So like 1.14. So 1.1447. We'll go to 4 decimal places, which means if now our model, if we plug all this back in, we get y is equal to 80 times 1.1447 by approximately how much in percent is the deer population increasing every year? Like if this number is 1.14, what does that mean about like the rate of increase every year? Because 1 would be it doesn't change. Yeah, Josh? Excellent. It increases by like 14%. So our final answer, if we write it as an algebraic function, would just be n of t is equal to 80 times 1.1447 to the t power. All right, and then you can always check your work by like plugging that back in. So 80 times 1.1447. All right, in 2016, that would be year 0. We get 80, or 2006. And then in 2012, that would be 6 years. The population should be 180, and it's very close to that. It's not exactly because I rounded this right here. All right. So that's the end of the video. I'm going to pause it and record it and all that stuff and upload it. Have a nice day.